We've learned about the Euler method. We've learned it's a standard example of a numerical method for ordinary differential equations. And we've seen also a few computational examples. What we've seen from those computational examples is that as we decrease the step size and let the Euler method run over a certain time interval, the numerical approximation for our ordinary differential equations get better and better. That has been just an observation, which is fair enough as a guideline. But in numerical analysis, we would like to understand how good our approximations actually are. We would like to have an estimate how good the approximation is. In other words, we would like to have a quantitative statement that tells us, okay, if I've got this and that step size and these and those properties of the ordinary differential equation, then the error is going to be at most this and that upper bound. There's quite a variety of such statements throughout numerical analysis for all sorts of numerical methods. And in this video, we discuss the Euler method and its error analysis. In particular, this observation that the approximations get better and better as the step size decreases will be put onto like a solid footing in this video. Okay, so what do we actually try to accomplish? Well, we are concerned with a Cauchy problem. Suppose the Cauchy problem is u prime of t is equal f of t and u of t, where we have the initial condition u of t naught is equal u naught, and we generate approximations for this Cauchy problem by the Euler method. So at every time step tk, we approximate the function u, the solution u, by uk, and these uk are defined recursively. uk plus 1 is defined in terms of uk plus h times f at tk and uk. And here in this case, tk is defined as t naught plus k times h. So we've got a sequence of time steps, t naught, t1, t2, t3, and so on. And at each of those time steps, we produce approximations u naught, u1, u2, u3 for the solution u at those time steps. And what we would like to understand is how good is the approximation of u at time tk by this approximation uk, which has been produced by the Euler method. The error at time t of k is also called the global discretization error, and we write ek equal u of tk minus uk for this global discretization error at the kth time step. I will continue calling it global discretization error. Some people call it global truncation error. This is really just about like personal preference. Now, for the error analysis, we need to impose a few assumptions. On the one hand, we impose an assumption that should look very familiar to you at this point. Namely, we make an assumption on the right-hand side f. We assume that there exists an L greater equal 0, such that for all times t and all vectors u and v from r to the n, we have that the distance between f of tu and f of tv is bounded from above by L times the distance of u and v. More precisely, the Euclidean norm of ftu minus ftv is bounded from above by L times the Euclidean norm of u minus v. That is the first assumption. And the second assumption is that u has second derivatives and that the second derivatives of u remain bounded throughout all times. And we let m be the maximum of the second derivatives that are assumed by u. So we assume that m is an upper bound at any time. Okay, with these two ingredients, let's get started. The idea of the proof is that we bound the error at time step k plus 1 by the error at the previous time step, the kth time step, plus some additional terms. Now let's begin with the Taylor approximation. So we take a look at the function u and take the Taylor approximation around the time step tk. Using what we already know about Taylor polynomials, we can now tell that u at time step k plus 1 is the same as u at time step k, it's a kth time step tk, plus h times u prime at time tk, plus h squared over 2 times u prime prime of xi, where xi is in between t of k and tk plus 1. This is really just a Taylor series. And I've used here that h is precisely the distance between tk plus 1 and tk. This is the first order Taylor approximation. And the last term, h squared over 2 times u prime prime of xi, is just due to the error theorem that we already know for the Taylor polynomials. Okay, having derived this identity, I use what I know about u prime, namely that it is equal to the right-hand side of the differential equation. So the next step, I replace u prime of tk by f of tk, u of tk. I'm going to leave it like that and shift my attention now to the Euler method. So in the Euler method, we have that uk plus 1 is defined as u of k plus h times f of tk u of k. So we've got a formula for u at time tk plus 1 and a formula for u k plus 1. And these two formulas look a bit similar. So now I take a look at the distance between u of tk plus 1 and uk plus 1. That's precisely the error that I want to approximate. So I take a look at u of tk plus 1 minus uk plus 1, and just plugging in these two formulas for these two terms that I've derived just now, I get that this distance, the approximation error at time k plus 1, tk plus 1, is the same as u at time tk minus uk plus h times f of tk u of tk minus f of tk u of uk plus that term from the Taylor formula, namely h squared over 2 times u prime prime of psi. Now let's take a look at this long formula. On the left-hand side, I've got the error at time step tk plus 1, and on the right-hand side, I've got the time step at tk. I've got the approximation error at time tk, and then plus some other stuff. Okay, that gets us a bit closer to a recursive formula for the approximation errors. So if we take the Euclidean norm on both sides, and on the right-hand side apply the triangle inequality, then we get the following upper estimate, namely the error k plus 1 is bounded in norm by the Euclidean norm of the error k, the error at time step tk, plus h times the Euclidean distance of f of tk u of tk and f of tk uk, plus h squared over 2 times u prime prime of psi. Now to improve this a bit further, this distance between the two values of f can be bounded from above by using this inequality that I assume for the function f. So that Euclidean norm here of f at tk u of tk minus f of tk uk can be bound from above by L times the distance of u of tk minus uk. And on the other hand, u prime prime of xi can of course be bounded from above by just take the maximum of u prime prime over the time interval from tk to tk plus 1. So using these two simplifications, I get the slightly larger upper bound, the Euclidean norm of ek plus L times h times the Euclidean norm of ut at tk minus uk plus h squared over 2 times the maximum of arc psi between tk and tk plus 1, where it takes the maximum of u prime prime of xi in Euclidean norm. Okay, next we recognize that this distance in Euclidean norm u of tk minus uk is just again the approximation error ek. Let's meet the next line where I've simply substituted now the definition of ek being the global discretization error at time tk, and the next line I just summarize these two terms. So I get in total up to now that the approximation error at time step tk plus 1 is bounded from above by 1 plus LH times the approximation error at time step tk plus h squared over 2 times the maximum of u prime prime over the time interval from tk up to tk plus 1. Okay, so this already looks like a recursive formula. Okay, now to simplify this a bit further, we use the fact that u prime prime can always be bounded by m in Euclidean norm. And substituting that, I get that the Euclidean norm of the error k plus 1, the global discretization error at time tk plus 1, is bound from above by 1 plus LH times the Euclidean norm of the error ek plus m over 2 times h squared. Okay, we got this recursive formula that gives us upper bounds for the errors at the different time steps, T0, T1, T2, and so on. So we already know that the approximation error at time step T0 is equal to 0 because the differential equation and the Euler method start at the same initial value. So the error at time step T0 is equal to 0. In particular, the error E0 is just vanishing. Okay, now let's get an upper bound for the error E1. Now using that E0 is equal 0, I get the upper bound that the Euclidean norm of E1 is bounded from above by m over 2 times h squared. Now let's use this recursive formula again for the second error, E2. So the Euclidean norm of E2 is bounded from above by 1 plus LH times the previous error, E1, in Euclidean norm, plus m over 2 h squared. And plugging in the upper bound I've already derived for E1, I get 1 plus LH times m over 2 h squared plus m over 2 h squared. Okay, and next I plug in this upper bound for the norm of E2 in the formula that I have for the norm of E3. So the Euclidean norm of E3 is bound from above by 1 plus LH times the Euclidean norm of E2 plus m over 2 h squared. And plugging this in, I get that this is bounded from above by 1 plus LH squared times m over 2 h squared plus 1 plus LH times m over 2 h squared plus m over 2 h squared. So we begin to see a pattern here. For example, if I try to get an upper bound for the Euclidean norm of E4, the error at time step T4, then the upper bound that I get using these substitutions is 1 plus LH cubed times m over 2h squared plus 1 plus LH squared times m over 2h squared plus 1 plus LH times m over 2h squared plus eventually m over 2h squared. So more formally, I can use an induction argument to show that the error at time step tk in Euclidean norm is bounded from above by the following expression, namely I sum up from j equals 0 up to k minus 1, 1 plus LH to the jth power times m over 2h squared. Okay, what's nice about that formula is that it involves only a few pieces of information about the differential equation, about the original Cauchy problem. So we need the constant L, we need the upper bound M, then we need the number of time steps that we are concerned about, and the step size h. However, this upper bound is not yet a closed formula. For example, we have got the sum here, and the more time steps we take, the larger the sum seems to become. So in order to get a nice closed formula, we need to work a little bit harder. So in order to get a formula that is actually useful, to get an idea about the behavior of the Euler method, we need to use a result from analysis. Namely, that huge sum there, where I sum up 1 plus LH to the j's power for j going from 0 up to k minus 1. That sum can be bounded from above by an expression that is a bit more handy in practice. Namely, I can use the upper bound 1 plus LH to the kth power minus 1 divided by LH. Now that inequality looks a bit like I'm pulling a rabbit out of my hat, or as if I'm applying sort of a cheat code. But that's what you do in analysis. In fact, this inequality might be known to you if you've already taken a reanalysis class or maybe even a calculus class. Namely, it's a formula for the partial sum of the geometric series. Equipped with that, I can simplify my upper bound for the error at time tk. Namely, the Euclidean norm of ek is bounded from above by 1 plus LH to the kth power minus 1 over LH times m over 2 times h squared. With a few rearrangements, this can be rewritten as m over 2l times h times 1 plus LH to the kth power minus 1. Okay, next I pull off another inequality that is known from calculus or reanalysis, namely 1 plus LH is bounded from above by the exponential of LH. Plugging that in, I get the following upper bound for the kth error in Euclidean norm, namely m over 2l times h times exponential of k times LH minus 1. And then finally, k times h, that's just the distance between the time tk and t naught. So this upper bound can be simplified a little bit to m over 2l times h times exponential of l times tk minus t naught minus 1. And that's precisely the upper bound that I've been looking for. Before we indulge deeper into the mathematics of the error estimate for the Euler method, let's have another look at a picture. What you see here is the numerical approximation of the solution of a differential equation, namely u prime of t equals v times u of t, with initial condition u of 0 is equal to 1. And these different approximations are derived from the Euler method, taken with different time steps. For example, at the very top you have this red line, which basically looks like the exponential of 3 times t. And suppose I'm interested in the solution of the time interval from 0 to 1. The solution, of course, is the exponential of 3 times t. And what you can tell is that the red line here is already very close to that solution. In fact, it's indistinguishable with the human eye in this resolution here. That line actually is obtained by an Euler method where the step size is 1 over 1000. On the other hand, we've got different step sizes here. For example, 1 over 4, 1 over 8, 1 over 16. As you can tell, as the step size decreases, as I keep doubling the step size, these curves get closer and closer to the actual solution. Let's suppose I don't know the solution and I have to trust the Euler method. And let's suppose I'm interested in the value of the solution at time t equal 1. That's on the very right here. As you can tell, as the step size decreases, the approximations get closer and closer to the solution, which is the exponential of 3, which just happens to be roughly 20.08 and then some. In the first curve here, where the step size is 1/4, the time t1 is assumed at the first time step t4. In the second curve, where the time step is 1/8, here in yellow, time t equal 1 is assumed by the time step t8. And in the green curve, slightly above there, you've got the time t equal 1 being assumed at the time step t16. The error estimate that we have derived so far tells us how large is the error at the time steps tk. But as you already see from this picture here, when we plot the solutions, the approximate solutions, then we not only take a look at the time steps, these discrete time steps, these ticks on the time interval, but we're also actually interested in the entire time interval. So for example, you see here that I have these polygonal curves, which are constituted by line segments, and actually I'm interpolating between the time steps. For example, if I have got the resolution h equal 1/4, okay, I compute this approximate solution at time steps 0, 1/4, 1/2, 3/4, and 1. And for example, in between these time steps, if I want an approximation at times between these time steps, I simply use linear interpolation. And just to complete our error analysis, let's also do the error analysis that I get for the intermediate times between these interpolation points. Okay, we have derived error estimates at the time steps where we perform the Euler method. So for example, here I have time steps tk and tk plus 1. We already have error estimates, but what can we tell about approximation error estimates between these time steps? So let's suppose I am interested in approximating the exact solution at a time t between tk and tk plus 1. Now, typically we use linear interpolation between these time steps to get an additional approximation, to get an approximation of the solution u between these time steps. So to formally define that, let tau be a number between 0 and h, and consider the number uk plus tau times f of t uk. That's a linear interpolation between the values uk and uk plus 1. So instead of going like the full step size h, I only go step size tau, which might be smaller. And we use this as an approximation of the solution u at time tk plus tau. Okay, so what is the error in that case? What is the error of this approximation? That error analysis is actually a bit similar to what we've done before. So we begin again with the Taylor polynomial. Using the error theorem for Taylor approximation, we see that the solution u at time tk plus tau can be written as u of tk plus tau times u prime of tk plus tau square over 2 times u prime prime of xi. The xi is a number between tk and tk plus 1. And again, I can plug in the differential equation. So I get that I simply use that u prime of tk can be written as f of tk u of tk. Okay, next we do a bit of inequality fighting. So this error at time tk plus tau, which I want to estimate in Euclidean norm, just plugging in the formula that I have for the Euclidean norm of ek, I get the following upper estimate, namely 1 plus L times tau times m over 2L times h times the exponential of L times tk minus t naught minus 1 plus tau square over 2 times m. Okay, what follows is only some algebraic manipulation. I take this vector 1 plus L times tau and pull it into the brackets. So I get m over 2L times h, and then times 1 plus L times tau times that exponential minus 1 minus L tau, still plus tau square over 2 times m. Next, in this first occurrence of 1 plus L tau, again apply this upper estimate 1 plus L times tau from above by exponential of L times tau. And I also pull out this minus L tau from this bracket. So I get the upper bound m over 2L times h times exponential of L tau times exponential of L times tk minus t naught minus 1. And then minus L times tau times m over 2L times h plus tau square over 2 times m. Now we can simplify a little bit. For example, I can summarize these exponentials, and I get the exponential of L times tk plus tau minus t naught. And I can also simplify the terms outside of the bracket. So what I get in the end is m over 2L times h times the exponential of L times tk plus tau minus t naught minus 1. And then outside the bracket, minus m over 2 times tau times h minus tau. Okay, now one more nasty trick is that h minus tau, of course, is non-negative. So this term at the end that I subtract is certainly non-negative. So if I just skip it, if I just remove the term, then I get an upper bound that is still valid. So I can bounce this entire stuff from above by m over 2L times h times the exponential of L times tk plus tau minus t naught minus 1. And what we now recognize is that this error estimate looks very similar to the error estimate at the discrete time steps. But we've derived it here for the intermediate time steps, for the times intermediate between the time steps. And that's precisely what we wanted to achieve. Everything we've done so far remains true if you only work over a finite time interval. In fact, working over a finite time interval will be the most practical case, as opposed to working over an infinite time interval. I've only postponed that restriction in order to keep the presentation as simple as possible. Now let's suppose that we have a time interval starting at t naught going up to t, and we're only interested in error estimates for times between the time t naught and the time t within this time interval. We need to slightly modify our two assumptions on the right-hand side f and the second derivatives of u. Namely, in this more general case with a finite time interval, we assume that there exists a number L, non-negative, such that for all times t from this time interval, and for all x and y, we have that the Euclidean distance of ftx and fty is bounded from above by L times the Euclidean distance of x and y. And moreover, we assume that u has second derivatives over the time interval, and that these second derivatives are bounded by some number m, which for example can be the maximum of the second derivative of u, the maximum of u prime prime over the time interval. So as you can tell, these are only some minor modifications of these two assumptions. And in particular, these two modifications do not affect what we've done so far in any sense. Okay, now we can finally summarize. So if we use the Euler method for the Cauchy problem, that is as follows, namely u prime of t is equal f of t u of t with initial condition u of t naught is equal u naught. And let's say between the discrete time steps we apply linear interpolation. Then as we've seen so far, the approximation error at any time t between t0 and t within the time interval is at most m over 2l times h times exponential of l times t minus t0 minus 1, where the two constants l and m are just as I described previously. Okay, so we have got this error estimate, m over 2l times h times exponential of l times t minus t0 minus 1. And that looks like a complicated formula. So I would like to spend a few minutes explaining the significance of each of those terms. So in order to get a feel, so to speak, for what this error estimate actually means. So this error estimate depends on a number of variables like m, l, h, and t. So one thing we can tell already is that this error estimate decreases in the step size h. So as I, for example, keep reducing the step size by 50%, halving the step size, so will the upper bound also reduce by 50%. And that works well with our intuition that as the step size decreases, so does the error actually decrease. So in particular, also we have got a working method. Just reduce the step size as much as necessary and we get an approximation as good as we want. Okay, then again, we see that this estimate actually increases in the time variable t. As t gets larger and larger, so will the exponential in the second factor grow larger and larger. This sort of matches the intuition that, in general, when we apply the Euler method to get a numerical approximation, at the beginning, the approximation is perhaps reasonable, but as the time grows larger and larger, we kind of lose track of the original solution. In fact, what this tells us is that the approximation error will grow exponentially as the time increases. So for very large times, our approximation might be completely useless. We also see that this error bound increases in m, which is a bound in the second derivative of u. The interpretation is that if u has very large second derivatives, then in some sense the solution experiences strong accelerations throughout its evolution over time. And as you can perhaps imagine, if a solution experiences strong accelerations as it evolves, it will be difficult to keep track of it by a numerical approximation. We have to use a very fine time resolution to keep track of all the sudden accelerations that the solution will experience. And this constant L, which we might call stability constant of f, for the lack of a better term. The role of L here in this error estimate is a bit intriguing, because on the one hand, in the first factor, we have got L in the denominator. The first factor actually decreases as L gets larger, but on the other hand, in the last factor, L is in the exponent of E, so that term actually increases as L gets larger and larger. So what happens if L increases or decreases? Well, it's perfectly fine if you don't know it. You might know it already if you've taken a class in real analysis, but what happens is actually that the growth of the second factor in L, the growth of the second factor, the exponential growth, cancels out the 1 over L in the first factor as L gets larger and larger. So effectively, this error estimate will increase as L increases. L in some sense measures the stability of the right-hand side under small perturbations. So you might say it's also intuitive that the error bound gets worse as L increases. Now, with all these error estimates, I've used that U has second derivatives. That, however, cannot be taken for granted, because from the differential equation itself, we only can tell that U has got a first derivative. U certainly has got a first derivative, otherwise we could not talk about this differential equation. But there are conditions under which we can actually guarantee that U has got a second derivative, and we can actually also get an upper bound for it. So let us suppose that f is differentiable. Let's take the second derivative of U in time. That just amounts to taking the time derivative of the right-hand side of the differential equation. So what we get is under the assumption that f is differentiable, is that u prime prime of t, the second time derivative of u at time t, is equal the time derivative of f evaluated at t and u of t plus the derivative of f in the second variable evaluated at t and u of t multiplied with u prime of t. We can again take the Euclidean norm on both sides of the equation, apply the triangle inequality, and take the maximum over all t and u, for example. And then we get that u prime prime of t in Euclidean norm for all times is bound from above by the maximum of the time derivative of f over all t from the time interval and all u, plus the maximum of the derivative of f in the second variable taken over all times t in the time interval and all u, multiplied with the maximum of u prime over the time interval. Depending on the specific differential equation, that estimate might already be helpful to get an upper bound for u prime prime. Getting an upper bound for the second derivatives of u is something that is done pretty much on a case-by-case basis. It might be difficult to make general statements about that.